Cruise ships look like floating cities, so the scary question feels obvious. If something goes wrong, what stops that entire city from going under? The answer isn't luck, and it isn't too big to sink. It's engineering that assumes damage will happen and builds in barriers, backups, and stability margins so one failure can't cascade into a total loss. Here's why cruise ships are so hard to sink in real life. The idea of unsinkable. When people say a cruise ship can't sink, they're actually describing something more specific than they realize. They mean that modern cruise ships are built to survive damage without immediately becoming a life or death situation. The ship is designed to stay afloat, stay stable, and stay controllable long enough for the crew to fix the problem, reach help, or evacuate safely if it comes to that. To understand why that's possible, you have to separate two different fears that get mixed together. First is sinking. That's a buoyancy problem. A ship sinks when it loses enough sealed space that it can no longer keep itself supported by the water. In simple terms, too much water gets inside the ship, replacing the air that was helping it float. Second is capsizing. Now that's a stability problem. A ship can still be floating, but if it leans too far and cannot recover, it can roll onto its side. People often imagine sinking as the only danger, but stability can become the bigger threat in the wrong conditions. Here's the important part. Big disasters usually aren't one moment. They are a chain. A breach happens, water gets in, and if it spreads into more spaces, the ship gets heavier and starts to sit lower in the water. That can lead to even more water coming in. At the same time, water inside the ship can shift weight to one side and increase the list. That can make containment harder and can change how the ship handles waves. So the real goal of modern ship design is simple. Stop the chain early. That's why this entire video can be reduced to 3 battles the ship is built to win. Battle 1. Keep enough spaces sealed so the ship still has buoyancy. Battle 2. Keep the ship balanced so it stays upright and predictable. And Battle 3, keep critical systems running so the crew can isolate problems, manage stability, and communicate clearly. Next, we start with the most basic layer of all, the physics of buoyancy, and why it's huge is not the real reason it stays afloat. Buoyancy in plain English. First things first, big isn't the secret. A cruise ship floats for the same reason a small boat floats, and it has nothing to do with being heavy. It floats because it displaces water. Picture the ship sitting in the ocean like a giant bathtub turned upside down. The hull pushes water out of the way. The ocean pushes back with an upward force. As long as that upward force is equal to the ship's weight, the ship stays on the surface. Now that's the clean, simple version. Now here's the part that most people miss. The ship doesn't float because it's made of steel. Steel is heavy. If you dropped a block of steel into the ocean, it would go straight to the bottom. The ship floats because the steel is shaped into a sealed volume filled mostly with air. That trapped air creates the space that ships need to displace enough water to stay up. So when you think about sinking, the real enemy is not water touching the ship. The enemy is water replacing air inside the ship. This is where the idea of reserve buoyancy matters. Reserve buoyancy is the ship's margin. It's the sealed volume above the waterline that exists as a buffer. If the ship takes on some water in certain areas, that reserve buoyancy is what prevents an immediate loss of flotation. In simple terms, it's the ship's ability to absorb damage without dropping to a point where it can't support itself. Now, yes, bigger ships often have more margin. They can have more sealed volume above the waterline and more internal space to distribute weight. But big is not the magic trick. If a ship were built as one giant open space inside, one serious breach could let water spread freely. And once water spreads freely, it doesn't just add weight. It changes balance. It changes the waterline. It can even expose new openings and cause more ingress. So the real reason cruise ships are hard to sink is not their size. It's the fact that their buoyancy is protected in layers. They're designed so that a problem in one area does not automatically become a problem everywhere else. And the core method for doing that is the single most important interior feature on a modern passenger ship: subdivision. Because once you divide the ship into many sealed boxes, you stop water from turning the whole ship into one connected swimming pool. Now go inside the ship, because the real reason cruise ships resist sinking is subdivision: watertight compartments and doors that keep a breach from turning the entire vessel into one connected flood. Flooding doesn't spread like you think. Imagine a pipe bursts in your house. If every door is open and every room is connected, water doesn't just make one room messy. It ties the claim to the whole floor. A cruise ship is built to prevent that exact cascade. Inside the hull, the ship is divided into watertight compartments, sealed zones separated by watertight bulkheads. Think of bulkheads as internal walls designed to hold back water pressure, not just separate rooms. If one compartment starts taking on water, the design goal is brutally simple: sacrifice that space and save the rest. This is why a hole in the ship isn't automatically a sinking sentence. What makes it work is closure discipline, physical and procedural. Watertight doors are the obvious part. They're heavy, gasketed, and designed to seal. In an incident, the ship's response is often about isolating a problem area first. Doors close, boundaries are enforced, and water is denied a pathway to migrate through the ship. The faster the boundary closes, the smaller the flooded volume stays, and flooded volume is everything. But subdivision isn't only about doors you can see. A lot of protection is structural. Many ships have a double bottom, an extra layer beneath the lowest interior spaces, plus internal tanks and void spaces. Those layers create buffers that can reduce how quickly water reaches critical areas, and they also give the ship more managed spaces where water can exist without instantly invading living decks. Here's the key engineering idea that sits underneath all of this: damage stability. Cruise ships are evaluated on whether they can remain afloat and stable after specific flooding scenarios. Not vague, it should be fine scenarios. Defined assumptions about where damage happens and where compartments flood. The whole point is to ensure the ship can take a hit, contain it, and still have enough intact buoyancy volume to stay up. That's also why uncontrolled spread is so dangerous. Once water moves from one compartment to the next, you don't just lose buoyancy, you create uneven weight. The ship starts listing, and a list changes everything. It can increase flooding on the low side, reduce effectiveness of certain drainage paths, and turn what was a contained incident into a rolling stability problem. So the ship fights flooding the way serious facilities fight fire, by zones. You don't defeat the water by pretending it won't enter. You defeat it by limiting where it is allowed to exist. And that sets up the part that most people underestimate. Even if a ship stays afloat after damage, it still has to stay upright and predictable. Because the real nightmare scenario isn't only water inside. It's water inside plus a stability loss that makes every decision harder. Why these tall ships don't tip over. At first glance, a cruise ship looks like a skyscraper balancing on a bathtub. So the instinctive fear is simple. If it leans, why doesn't it just keep leaning? Because the ship is not top-heavy in the way your eyes assume. The visible part, the hotel decks, restaurants, balconies, theaters, take up a lot of space, but it's not where most of the mass lives. The heavy stuff sits low. Engines and propulsion equipment, generators, fuel, ballast water, machinery, and thick structural members. That low placement drags the ship's center of gravity downward, which is exactly what you want for stability. Now add the second piece, hull shape. When a ship starts to roll, the shape of the hull changes how buoyancy force acts on it. The water pushes up on the hull, and that push point shifts as the ship leans. Done right, that ship creates a restoring tendency, a kind of built-in come back upright behavior. It's not magic, It's geometry plus weight distribution producing a riding moment. Now, this is why cruise ships can move with waves without feeling like they're constantly one bad gust away from disaster. They're designed with stability margins so that normal wind, swell, and passenger movement don't come close to the limits. But stability has an enemy that's sneaky because it doesn't look dramatic. Moving liquids. If you have water sloshing inside a partially filled tank, it doesn't stay put. As the ship rolls, the water shifts to the low side, and that shift drags the center of gravity sideways. That reduces the ship's restoring ability. This is called the free surface effect, and it's a major reason ships manage tanks and flooding boundaries so carefully. It also explains why water inside the ship is not just a buoyancy problem, it's a stability problem. Flooding can make the ship heavier, yes, but more importantly, it can make the ship uneven. That's where ballast and trim management comes in. Ballast tanks aren't just extra weight, they're control tools. Operators use them to keep the ship level, manage stress on the hull, and maintain safe stability characteristics. After damage, stability management becomes a continuous calculation. How much water is where, what is shifting, and what actions keep the ship inside the safe envelope. And here's the sobering point. A ship can remain afloat and still be in real danger if stability collapses. That's why modern design treats stability like a first-class survival requirement, not a comfort feature. So far, you've seen how ships resist sinking by sealing spaces and resisting dangerous tilt. The last layer is what happens when systems start failing, because surviving damage is also about staying operational under stress. When one system dies, another takes over. If a cruise ship were built like a normal building, a serious incident would be simple. One broken main system and everything goes dark. Ships don't have that luxury. A modern cruise ship is designed around the assumption that something important will fail at the worst time in the worst place. So instead of one backbone, you get multiple spines. Redundancy isn't a bonus feature, it's the survival concept. Start with power, because power is control. A cruise ship does not run on a single generator with a single route to every vital device. It uses multiple generators feeding a distribution network. If one generator drops off, another can carry essential loads. If one section of the electrical system is compromised, the ship is designed to isolate it so it doesn't drag everything else down with it. Then there's separation. This matters as much as having extra equipment. Redundancy is weak if all backups sit in the same place. That's why critical machinery, switchboards, and control pathways are often arranged so one localized incident doesn't wipe out every copy at once. The goal is to avoid one-hit total failure. Now zoom in on what essential really means in an emergency. Comfort systems can degrade, and it's unpleasant. But survivability depends on a smaller set of functions: detection, communication, emergency lighting, navigation support, pumping capability, and the ability to monitor stability and flooding boundaries. These are the systems the ship protects first, because they are what let the crew do their job under pressure. That leads to the quiet part people underestimate: monitoring and automation. Ships are loaded with sensors and alarms because a ship can't wait for a human to notice something is wrong. Flooding, fire, overheating, abnormal electrical loads, watertight door status, tank levels. These are tracked so problems get called early when containment is still possible. Early response is not about drama, it's about preventing spread. And redundancy isn't only hardware, it's also procedure. Checklists, cross-checking on the bridge, drills, and clear chains of command. The engineering gives the crew tools. The crew turns those tools into time. Here's the punchline. The ship doesn't have to be perfect. It has to be resilient. It can take damage, lose a component, even lose a whole slice of capability. and still remain afloat and stable because the design prevents failures from linking up into a single unstoppable cascade. Now, once you understand that, the story stops being, can it sink, and becomes, can it keep control long enough to contain the problem? That's where damage control moves from theory into real-time action. The moment water gets in, the clock starts. A breach isn't instantly a disaster. It's an emergency with a timer. The ship's entire safety logic is built around one idea: detect fast, isolate faster, then stabilize the situation before it spreads. And that response isn't improvised. It's structured, drilled, and tied directly to the ship's layout. First comes confirmation. It sounds obvious, but in a real ship, "there's water" is not specific enough. The crew needs to know where it is, how fast it's coming in, and which compartments are affected. Is it a small leak or an active ingress? Is it contained to a lower space or threatening to climb? Those details decide everything that follows. Then comes isolation, because isolation is what turns a problem into a controlled problem. Watertight doors and boundaries become the main lever. Close the right doors and you prevent water from migrating into adjacent compartments. If a compartment is going to flood, the best outcome is that it floods alone. The ship can often tolerate that. It cannot tolerate the same volume spreading unchecked across multiple spaces. After isolation, pumping becomes the tool, not the solution. Ships have bilge and draining systems designed to remove water, but pumping is only effective if the water ingress rate is manageable and the boundaries are holding. If water is pouring in faster than it can be pumped out, the purpose of pumping shifts. Slow accumulation, protect critical spaces, and buy time while other actions are taken. Now comes the part passengers rarely think about: stability management. Water inside the ship changes weight distribution. If flooding is uneven, the ship can list. A list can worsen flooding on the low side, change how water flows internally, and complicate movement on board. So crews continuously monitor list and trim, and they act to keep the ship within safe stability limits. That can mean shifting liquids, managing ballast, or controlling which spaces are allowed to flood versus which must remain dry. This is also why containment and stability are inseparable. A ship can survive flooding if it's contained, but stability can collapse if water is allowed to move freely or accumulate asymmetrically. While all of that is happening, there's a parallel track that matters just as much: passenger management. Not because passengers are the problem, but because human movement affects the ship's ability to operate. Corridors need to stay clear. Critical doors must not be blocked. Muster routes must stay usable. The crew's instructions are designed to keep the ship's internal flow functional, because a ship emergency is a logistics emergency. That's the real difference between a controlled incident and chaos. The ship is trying to run a plan under stress. And here's the best part of the whole story. Most of the time, the ship never needs to run that plan at full intensity, because the strongest safety layer is upstream. Before flooding control, before redundancy, before damage response, there's avoidance. The ship's bridge and routing systems work every day to prevent the situation from happening in the first place. The safety work you never see. Most cruise ship safety happens on days when nothing happens at all. Long before a ship ever needs watertight doors or pumps, the bridge team is doing a quieter job, keeping the ship out of situations where damage becomes likely. This is why many serious incidents don't start in the middle of the ocean. They start near hazards, coasts, narrow channels, busy traffic lanes, and ports, where the margin of error shrinks. Weather is the first filter. Modern voyage planning isn't set a straight line and go. Routes are adjusted around forecasted sea states, wind, and storm systems to reduce exposure to the kind of conditions that stack risk. Even when a ship can physically handle rough seas, avoiding them protects stability, protects passengers, and reduces the chance of knock-on problems. Navigation is the second filter, and it's built on cross-checking, not one magic screen. The bridge uses multiple sources of information, positioning, charts, radar, and traffic awareness to confirm where the ship is, what's around it, and how fast closing distances are changing. The point isn't that technology is perfect. The point is that different tools catch different errors before they become contact with something solid. Speed management is the third filter. In open water, the ship has room and time. Near land, speed becomes a risk multiplier. Slower speed means longer reaction time, smaller forces in a collision, and more control in tight turns. It's boring, but it's decisive. Ports add another layer: local knowledge and controlled movement. In many places, ships use local pilots and tug assistants because docking a massive vessel is not a driver skill moment. It's a controlled operation with procedures designed to reduce grounding and contact risks in confined spaces. The most important thread through all of this is human discipline. Procedures, checklists, and bridge teamwork exist because the ocean doesn't forgive close enough. That's why rules and training standards, often shaped by international bodies like the International Maritime Organization, focus so heavily on preventing small errors from snowballing. Now, all of that prevention explains why the dramatic question, can it sink, is usually the wrong starting point. The better question is, how many layers have to fail before we even get close? If this breakdown helped you understand how cruise ships are engineered to survive the worst, hit like and subscribe for more straight, practical explanations like this. And drop a comment. What part surprised you most? Watertight compartments, stability, or redundancy? Thanks for watching, and if you want to keep going, click the video on your screen right now. Your voyage is just beginning.